Good evening, guys. Uh, Welcome to the day 9 of the training in FPGA development. So, till now, we have discussed different projects on developing on the FPGA. So, coming from basic and OR gates, we have developed using IP integrator, and also we have developed a software processor on the FPGA architecture. So, those are available in the previous classes. So, from today, we will try to introduce ourselves to the Verilog HDL programming. So that is the major step in the entire FPGA development. So if you understand the Verilog HDL and the structure, how to write the Verilog HDL, then you will be familiar to develop different types of applications and projects on the FPGA board. So uh, today it will be like most of the time it will be like a recap on what we have done in the last previous classes, and from there we will go towards the learning of advanced stuff in the Verilog HDL. And in the Verilog HDL, it will be like example based, projects based learning. So, whatever you learn, the syntax or the script that you need to write in the structure in the Verilog HDL, that you can be implementing with the smaller example logic circuits like designing mux or designing memory controller, any other basic examples. So, with that being said, so let us enter into our day 9 of the training. And I am happy to see you all again on day 9. So please be consistent and also do complete the recordings or the class lectures as per the schedule, as I'm going to be removing them from the YouTube as well for the limited access. So if you want recordings, you can purchase anytime. So thank you. And let us go to the today's agenda. So what is today's agenda? It is like summary on the FPGA architecture. That's what we have developed. Let us understand the architecture again and recap on the FPGA development flow. Examples of FPGA applications you should be knowing, and recap on the project examples that we have developed. I'll vaguely introduce to you to the previous example projects so that you have developed. Those are not examples actually. That is the way you can develop with the EDA tools using Vivado. So it's like familiarizing ourselves to the project, and then differences between Verilog HDL and VHDL. I'll try to have some differences between both of them. I'll try to explain, and what are the Tcl and Perl scripting. So very basic command languages that are mostly used in chip design industry in terms of EDA automation. So let us go to the today's lecture. So what is FPGA? FPGA is a hardware board or hardware chip that can be developed on the basis of applications that we desire. So yeah, it's like FPGA is a chip built with numerous logic cells that are divided into configurable logic blocks, switching matrix, and IO blocks. So there are major three components of FPGA which you can be dividing with configurable logic blocks, CLBs we call it as, and switching matrix and IO blocks. Every time you think of FPGA chip architecture, think of these three things. One is CLBs. I'll be explaining in the next slides as well. One is CLBs, one is switching matrix, and another one is IOBs. So you should be very familiar in developing all these three components in the FPGA architecture. Coming to the next point, FPGAs are used mainly for designing our own logic functionality for the application. So if you have a CNC machine or if you have any application in the industry, a small example is to run the chain belt from position A to B. The chain rotates and you will be seeing the chain rotation in this way. And for the FPGA, if you design, okay, for 10 nanoseconds or for 10 seconds, the chain should be moving in this left to right direction. And if you write another command in the FPGA architecture stating, okay, after 10 seconds, from the 11th second to 21st second, the chain should be moving from right to left in this way. So these are the basic applications in the industry. Those can be programmed on the FPGA architecture. And for the rest of the years, the FPGA will be doing the same task, moving the chain from left to right and right to left. That's one kind of application in the industry. And you can also design some robotic arms and some welding operations using FPGA architecture. Then come to the configurable several times. So it FPGA can be configurable several times. Why? Because once the architecture you have developed, you can reset it. I mean, you can erase the architecture on the FPGA chip, and then you can rewrite the program several times by the use of different sets of application in the structure of Verilog HDL. So what you have to do is, if you have written 100 lines of code stating one particular process, and you can extend the code or you can erase the code completely on the FPGA chip. That's nothing but resetting on the FPGA chip, and then you can reprogram it for the next set of applications. So first, if you have applied and if you have installed FPGA chip with particular application for the first 2 to 3 years in the industry, then you can upgrade the architecture without changing any chip, without changing any hardware. You can just rewrite the program in the advanced level, and you can increase the lines of code from 100 to 150 or 100 to 1000. Then you can run 1000 lines of code with a new architecture embedded on the FPGA. So that's an advantage. That is the reason you can reprogram the FPGA several times. So in the field itself, you can program it many multiple times, and you can also upgrade the architecture from one core, single core to double core, or double core to octa core. So you can multiply or you can improve the progress of the FPGA architecture. So then major FPGA producing companies are Xilinx, Intel Altera, Cypress. Keep in mind, guys, Xilinx, we have it's under AMD. So in the Xilinx, you can see the AMD boards which have ARM Cortex architectures, and also Intel Altera. It has a architecture on its own, Intel architectures. And then Altera is the company which was acquired by Intel, such that all the hardware or the FPGA programs or chips made by the Altera boards are acquired by Intel now. So we can see the Altera DE2, DE4, DE5 boards available in the market, and Cypress is one other company same as Xilinx and Altera. So these are the points you should remember when you think of FPGA. Okay, we can be flexible with the FPGA architecture, and we can rewrite the program several times, and it can be configurable. What are the major components of FPGA? So FPGA has CLB, switching matrix, and IO blocks. And then FPGA chips versus ASIC chips. As you know, ASIC chips have a best example of mobile phones, laptops, and if they are made for one laptop, it's only made for that laptop, and you can't use that processor for any other architecture or any other board. I mean, that same kind of laptops, or you can take this chip from a laptop A and you can embed it into the second architecture of another laptop, but it's like only doing the operations of laptop. What it connects to the display, it connects to the memory, it connects to the Ethernet ports, all these things. So ASIC chips are basic examples of one time task, and if they are designed for one specific application like mobile, laptop, or personal computer, or any other chips in the industry, those are designed only for that. But FPGA chip, they can be used in several ways. They can be used as microcontrollers. For example, any kind of microcontroller application like Arduino can be run on FPGA architecture. You can build a processor. That's what we have discussed in the previous lecture. And then from that architecture, you can take out this entire architecture and you can erase it. You can remove the first embedded architecture, and you can reinstall the second version of the architecture with the upgrade version of it. So this kind of flexibility is available in FPGA chip. That's the reason FPGA chips are also widely used, and the effect of manufacturing chips in the of FPGA architecture are very cost effective. But in the ASIC, if you have designed it, and those are only designed for fewer years of generation, and in the upcoming generations and in the upcoming technologies with the lower node, lower 7 nanometer or lower technology nodes, you can't upgrade the ASIC chips that were built 2 years back. But FPGA chips, you can use the functionality and you can upgrade the functionality depending on your latest technologies. So that's the another advantage of FPGA chips. So you can remember these points. FPGAs are easily configurable several times, and one FPGA chip can be used in different applications according to the user specification. So once manufactured, can be used many times. That's what the advantage, major advantage of FPGA. And ASIC chips are designed according to specific application and cannot be redesigned once you design it for the ending purpose, and it is done for it, and hence costly to make more designs. But the major advantage of ASIC chips over FPGA chips are they can be processed very fast. Like the process of application in the ASIC chips are way more faster than FPGA applications. So they compete on a line to line edge. So it's based on the architecture you develop on FPGA, and you can take an FPGA chip and you can completely turn it into an ASIC chip. But again, if you turn it into an ASIC chip and make it faster, you can reset it and you can make another version of the FPGA chip as well. So in certain specific domain of the industries, we use ASIC chips for setting the standards like speed, performance, and area and power optimization. And in the other segment of the industry, in manufacturing or any other domains, we take the examples of FPGA chips and we apply them mostly for the testing purposes as well. So yeah, those are the differences between these things. And architecture inside FPGA chip. Let us go deep into the components of FPGA chip. So we have a block called CLB, configurable logic blocks. Nothing but, let me explain. So this is the lookup table. This is the input some lookup table with random inputs 1 1 and 0 0, and these are the ports x1 and x2. So if these are the ports, and let us say if this is 0, now we have 1 0 0 1, that is the application XNOR application. And you also know, if you have 0 1 1 0, that is XOR application. Let me write from the beginning. So now let us consider we have input ports. These are the IO ports. So this is one IO port and this is another IO port, and we have LUT, lookup table. And in the lookup table, I'll explain the this thing later. And we have muxes. We have every time we will be having muxes and the logic cells. You might have seen in the earlier lectures that when we zoom in the implemented design, we will be seeing the logic gates, XOR logic gates or XNOR logic gates. And for that logic gate, machine will be understanding only the in terms of lookup table data. So this information is nothing but XOR applications. So for that XOR applications, let me change the value. So now you can understand it is XOR application, and right in input, and that is another input. This here we will call it as output. So this is output, and we have mux here. And whenever you have a value of 1 and 1, what you will be getting the value output as. So x1 is connected to the selection point. This is selection 1 and this is selection 1 from the input port of 1. And let us call this input port of the second pin, call it as section 2 for the mux 2. This is the second level. Every time we call it as levels of muxes. So it is like levels of design implementation. So it is like if you take it as level 1 and if you take it as level 2, in the level 1 we have two muxes. This is M2, let us call M1, and it is M3. So based on the selection input, if the selection is 1, I am explaining the functionality of multiplexer. If the selection input is 1, then this second input of the mux is selected and it is pushed forward. And if the selection one second, if the selection is if the selection input is 0, if the selection input is 0, this mux, this input is selected and your output is 0. Got it, guys? So every time it is 0 and 1. Don't get confused with 0 and 1 here. Every time you will call it as selection S1 and S0. So this is nothing but S0 selection and S1. I'll try to explain the multiplexer application again. But as of now, you understand a very simple thing. When you have the input 1, for example, input port 1, here you will be seeing the data 1 and also seeing the data 1, and because of the selection, this selection is 1. Based on the selection 1, the 1 input is taken. So this second input of the mux is selected. So that is what the reason of selection port is, nothing but selecting which input to be taken. So now it is 1 and here it is 1, right? So now it is 1. Now the output is 1, and based on the input of x selection 2, if the selection 2 is 0, if the selection 2 is 0, let us take this example. This is 0th selection and this is one selection like S0 and S1. Now the selection is taken from this port. So till now it is 1. Forget about all these levels. So every time you see the mux and what is the selection port selected. So first step is think about the mux, and second step is think about the selection, and in the selection think about the input. What is the input here? This one is we have got this one from this, and also this one is input. So the third point is what is the input given by the port. So that is 3. 1, 2, 3. So this is output we will be getting. If we come back in the initial stage, first we need to select the port. What is the port data that is given in, that is 1. For example, it is 1. And now this goes to the multiplexer here, and the multiplexer selection is 1, right? So the what is the input for the multiplexer? Second one is selected. And if it is 0, if the selection is 0, now this input is selected, 0th selection and 1 selection. So you can multiplexer with that. So if the selection input is 0 now, so this is first point, and now it will go to the selection port, and this is 0, and here you should consider the 0th selection. So now what is the 0th selection output? It is 0. The data is taken from lookup table. Don't forget this. What is the input for the multiplexer now? This is let me write. When I say 0th selection, it is S0. So S0 and S1. So now the data is 0 here and the output is 0. So in the same way, if we have 0, right? 0 is the selection port. So here the 0, and here it is S0, and here it is S1. So what is the data to be selected? Which port is enabled now? This selection port is enabled. So hence data is 1 here. So this one is pushed forward here as the output as 1. So now 0 and 1. Now whatever the input in the x2, if it is 1, so here we have again selection 1 and selection 0. So why do we mention S0 and S1? That is how multiplexers are all designed in the combinational logic circuits. It is not S1 and S0, S0 and S1. If 1 is the input given to this selection line, this is the 1 here, and so now S1 is selected. If 1 is the input, S1 is selected. So this will be the input to the multiplexer. Hence 1 is taken and now output is 1. Understood, guys? And if 0 is taken, I'll explain. So if 0 is taken, forget about this one here, and now if 0 is taken, now selection will be S0, not S1. So the data will be given as 0 will be carry forwarded, and this is not output, and this is 0, and this is the input for D flip flop, and output we will get as the desired output as Q in this state. So that is how these configurable logic blocks are designed. So basic structures are we have ports, basic components of configurable logic blocks are ports, lookup table, multiplexers, nets are nothing but connections. These are the interconnected nets between two elements, and then after nets we have flip-flops, any flip-flop, but we consider only D flip-flop, which is more advantageous. So and then output ports. So let me mention, these are the input ports and we have output ports. So these are the components of configurable logic blocks. This is how it all appears. So understood, guys? Come back to this lecture again, and I will also be explaining about configurable logic blocks in the later sessions. Don't worry. So next let us move on to the switching matrix. Switching matrix is nothing but it is a interconnection between two configurable logic blocks and all the two other elements. So these might be SRAMs, connected SRAMs, switching matrix, and you can have SRAM here. SRAM is nothing but lookup table. Lookup tables are stored in the SRAM modules, static RAMs, and these switching modules will be connected in this way between configurable logic blocks. How these are connected, and these can be seen. So what we are developing now in the FPGA, we are writing codes for configurable logic blocks. We are writing codes at switching models, and we are also writing codes at IO blocks. So we are designing all the ports, all the elements, all the components inside FPGA. What are the components? 1 CLB, 2 switching matrix, and 3 IO blocks. IO blocks I'll explain in the next video. How IO blocks will be designed. So what is the internal components available in the IO blocks? I will show you. So now switching matrix are elements which are used as connections between each of these SRAMs, CLBs. I mean, switching matrix can be used between two CLBs, and switching matrix are also designed between connection between two SRAMs. So and other elements as well, whatever elements you get it. So those can be seen like this. Yeah, you can see. So and now moving to the IO blocks. IO blocks are nothing but you can have tri-state buffers. So if this is the input one and you get the output, so this is how these are designed between the buffers by using buffers, and you can see IO pads. that we have discussed in the previous sessions. In the IO pads, these IO pads are connected with a IO block. So you need to design this IO block for uh, converting or for the connections between the switching matrix or CLBs to IO pads. In between, you have this IO blocks. Okay, so you have IO blocks. Now, understood? So next, this is what the internal architecture of the FPGA chip. So if you can see, if these are the ports that are available around the FPGA chip, inside you can imagine, you can see CLBs and switching matrix, CLB, switching matrix, and CLB and switching matrix. You just imagine inside the chip, you can see all these things. And now this entire chip you have designed, for example, you have designed a UART module, and that UART module can be taken to the USB interface. And USB and UART can be connected to USB protocols. So that program can be enabled by using IP integrator. You can use USB IP integrator on this, and one IP. So if you have developed USB IP intellectual property, you have enabled the architecture of USB IP to the FPGA chip, and now this USB is internally connected to the USB. So that is how whatever the intellectual properties architecture we develop on the chip, those are again connected through the PCB designs with the physical ports. Now, if you connect some pen drive to it with some names to be displayed on the LCD, so that pen drive data will be transferred over this USB connections, and with that USB protocol, so this chip will be taking that data and it will be connected to the display again. You will be writing display architecture again. So again LCD will be connected. So this is how the functionality happens, and this entire process can be done within nanoseconds. So that is the fastest, I mean, importance of the chip designs, which are central processing units. So in these central processing units, you will have clock, which will be processing the data according to the speed and performance. So again, clock pulses are nothing but electric analog pulses, where one can be 0 and 1s are the clock signals. So you can see this clock signal like square blocks going on. Sorry about the bad drawing, but it can be 0 and it can be 1, 0 and 1. In imagine this is a uniform clock pulse. Sorry about the drawing. If this is the uniform clock pulse, and you have one can be 3.3 volts, LV CMOS 3.3 volts, or one can be 5 volts. So 0 can be 0 volts. So again, this is in terms of digital reference. We have designed the clock for our own references for the data transmission and data processing. Signal processing. So this is the reference for signal processing. Just understand. But in general, the clock or the chip will be interpreting the analog pulses, analog current pulses, voltage pulses into the clock, and that clock can be understood by the chip. So in the later lectures, we will be discussing about all these elements in detail. While we are developing Verilog HDL, we will understand the clock and what are the different levels of Verilog HDL, which can design the components of FPGA chip. So let us move on to the development of FPGA flow, that we have already developed this, and now I am recapping everything. So today the lecture will be like a revision to you all. So what is the process of FPGA development flow? It will be like coming from HDL, we write we will take the specifications from the consumer or from the required head, and from that architecture we develop the uh, architecture using Verilog HDL. Why do we use Verilog HDL or HDL? Because these are the hardware description languages. HDL is nothing but hardware description language. What hardware you are developing? It's nothing but on the available FPGA chip that was manufactured, you are developing a architecture to it. Okay, so this architecture will be developed using HDL, and if you have done writing the HDL as we have done in the previous examples, then it is carry forwarded to RTL analysis, and in the RTL analysis all the errors or the syntax errors or the debugging errors, every error that if it is available in the HDL and if you have not mentioned the ports correctly and the functionality correctly and the processes, if you haven't begin and if you begin and if you don't end, so if there are any such kind of errors available in the HDL script that you have made, and if that is not compatible with the hardware architecture of the board that you have selected in the EDA environment, in the RTL analysis you will be finding all the issues, and in the RTL analysis you can rectify them by using the test bench embedding to the HDL. Test bench is nothing but it is again a file which is made for verifying and rectifying the errors by HDL using the test bench simulation. Test bench is a file which you can be using that for the verification of primary source. If this is the primary source Verilog HDL file, and by using test bench you can check the functionality of the working of HDL file. For example, if it is OR gate, you should test bench by giving inputs like 0 0 0 1 1 0 and 1 1. You should give the inputs for the OR gate input like x1 and x2. You should get the output as y, and for the y what you should be getting, for 0 0 you should be getting 0, and for output like for 0 0 you should get 0, and you should get 0 1. If it is 0 1 you should get 1, and if it is 1 0 it is 1, and again for 1 1 it is 1. So 0 1 1 1. So you should be seeing the output as 0 1 1 0 uh, 0 1 and 1 1. That is the output. So how do we test the HDL file? Okay, those HDL file can be tested using test bench VHDL file. So please understand this is the verification process in the HDL. So, and then after test bench you can run the synthesis successfully. By synthesis you can also see some simulation with the timing simulation charts as we have seen in the previous lectures. So, and then for the synthesis you will be adding constraints file, and in this constraints you can add the constraints according to your design. There will be physical constraints and there will be also some logical constraints including timing constraints, some logical constraints and some physical constraints and some timing constraints. In the timing constraints you can add clock constraints. So the clock frequency should be working under 50 hertz or 100 hertz. So there is no hard and fast rule, but you can declare the constraints based on the design specifications according to the HDL. So if you have mentioned clock as 50 clock frequency of operation as 50 megahertz, you can take this constraint timing clock time should be around 20 nanoseconds. That's how you can make it. So from the 50 megahertz of frequency of operation, you can mention the timing constraint like 20 nanoseconds. So in the physical constraints, you can also mention what is the temperature of operation. If it is beyond the temperature of operation, it should go to shutdown state. switch off state, and the abnormalities of the functionality in the chip processing will occur. And after synthesis, you can take synthesis is nothing but it is a major step where this HDL script, whatever you have written, how many OR gates or AND gates you have written, for all those logic cells, you will be assigning some libraries where that libraries are reference for the physical manufacturing in the chip processing. In the outside chip, in the chip, if you have OR gate, so for that OR gate connection, this library can be understood only after the synthesis. So now your script OR will be taken to the OR gate. So OR gate. So that OR gate is now understood by the chip, and now OR gate is enabled. So now you are writing only function. So function f of r. So that is function, but it is not gate. So what synthesis is doing, making this function or this script that you have written into the physical environment, into the gate level. So hence after synthesis you will be getting gate level netlist, and we will be using all the gates. And then now we will be implementing design with all the gates, ports, and after in the implementation, you will be IO planning, you will be placing. So machine will be doing all these things. Whatever EDA tool you use, that EDA tool, that EDA environment, design automation environment will IO plan, will place the cells, and will route. These all we have discussed in the previous lectures. Yeah, go check it in the previous lecture for the reference. After the implementation, check for the simulation, guys. In the simulation, you can find the output of the design implementation. As we have run the implementation successfully, we can open the design or the device, and if you zoom inside the device, you can see logic cells and all that are available. And in the simulation, if you find any error, right, if there is error, so sorry guys, let me check. Now this yes should go here, and this no should come here, and yes. Okay. Now if you see any error, right, you should be taking this entire design to the debugging stage, and then after debugging it should go to the implementation. So then again, after successful implementation and verifying all the errors, and if you rectify them from the HDL stage itself, then you can go to the simulation. And if you have successfully run the simulation without any errors, no errors, come back to the output bit stream. So hence we also generate bit stream that will be going to the final stage, where these bit streams are nothing but those are converted hardware files in terms of binary that can be understood by the architecture or any FPGA board. So when you flash this bitstream file onto the FPGA in the field, then your FPGA will work exactly according to the architecture you have developed using HDL. Understood, guys? This is the flow. Remember this as it is. And now let us go to the each step in detail. I'll quickly walk through all these steps as we have already discussed with the flow. So in the FPGA development flow, step one will be writing the VHDL or Verilog HDL. It doesn't matter in which language you develop the architecture using FPGA. It can be VHDL or Verilog HDL. Then this language is used to develop the design that can be interpreted on the FPGA chip. Next, FPGA development flow. In the second step, you will take the RTL analysis as we have discussed. This is the second step, and you can in this RTL analysis is verified and configured again according to the HDL. Now after this RTL analysis can be run through the test bench VHDL and Verilog HDL, and in the test bench it is again the same HDL file, but it will be used only for testing the primary source file or primary architecture, whether the functionality, logic functionality is applicable or used in a right way. according to it. So those type of functionality testing can be done using test bench VHDL file. It's majorly used for verification. So now we can make test bench files by using online compilers available in the market, but highly suggested methodology of writing test bench is writing on your own. Understand how to write test bench vectors or test bench files for your primary design source file, which is HDL. So based on the primary HDL file, you can generate the test bench VHDL by using online or by writing on your own. So we in our industry, we don't want to compromise our own primary source design file in the online compilers, because we shouldn't be giving the own data of the company to the outsourcing. So hence it is most required skill for writing test bench VHDL files or test bench vectors for the our own primary source design file. So the engineers who know these test bench VHDL writing, scripting, or Verilog HDL, if they are familiar with Verilog HDL and also writing test bench VHDL, so there are more chances in getting recruited using these test bench VHDLs. So then move on to the next step. It is synthesis. Now in the synthesis, according to the physical requirements of the design, all the library cells that are to be enabled on the FPGA chip are now connected with the functionality that you have written in the HDL script. So if in the HDL script, if you have designed a OR gate, and that for that OR gate you should have a physically available OR gate on the FPGA chip. So those two are connected. So in the synthesis, so you will be generating a gate level netlist file. What is the output of synthesis file? Output is nothing but gate level netlist file. This can be a question, guys, when you when you are in an interview. So in the constraints, so as I have mentioned, you can mention different types of constraints like specifying max delay, min delay, false paths. So these are the delays that you need to design, or that you need to constrain in the design for data flow or in the terms of clock pulses. So other constraints related to physical and IO pins can also be set, like only this set of IO pins can be used, or physical like temperature, or this type of if it crosses this type of temperature, it should go switch off, or entire data will be reset. So those are the physical constraints, and in the terms of physical constraints, you can also limit the area of usage. Only some particular block or some particular area of the chip you can use. Only those particular cells can be used. These are all the constraints that you will be getting in the complex designs when you work in the industry. So you will take some physical constraints from the higher team, and you have to design your entire architecture based on these constraints. So in the entire chip, I'll explain. So physical constraints can be like in the entire chip, if you are allowed to only use this area of the block, and whatever OR gate you have here, and only that OR gate should be used, and only you should enable this OR gate from the synthesis happening. So there are restrictions here. So hence you can take all these constraints. Then after applying constraints, you can go for the implementation. Implementation is nothing but you need to design the chip, like all these cells should be designed. They can be placed in this particular area, and this particular area, and this particular area, and all the remaining part is left as it is, and that is of no use for you. So now you have designed in these three particular regions of the chip, and that kind of placement of the cells is also a major part, and connections between these cells, and that connection is nothing but routing. So majorly you do place and routing. So placement and routing is the major part of designing implementation. So after this design implementation, according to the logic operations and specifications you made in the HDL file, you can go for the debug and error rectification. This can be the last step with error rectification. After error rectification and debugging, Now your file is ready to generate the bit streams. This is the step 8. Yeah, step 8. Step 8 is nothing but bit generation. So in this bit stream generation, it is used for bit streams, and you can develop this uh, bit stream file, and you can upload it on the FPGA hardware. So export hardware. We have done this step as well in the previous lectures. Thus entire FPGA functionality is developed onto the chip. This is a simple flow. Take a note of this entire flow diagram. It will be helpful for you. Now let us go to the examples of applications of FPGA, which FPGAs are wide range used in automotive industry, heavy machinery industry, communication devices, satellite communication, robotic applications, and Internet of Things. So you can see different applications of FPGA, and you can also build some basic example projects in this kind of industry applications. For example, in the automotive industry, you can take some CAN bus protocol and try to implement that CAN bus protocol on the FPGA chip. And also in the Internet of Things, right? You can implement AI, as some of you have asked me how to implement AI. So you can actually build a processor application on the FPGA architecture, and then build some AI program onto the processor that you have developed in the FPGA. It is like you can turn this FPGA board into a microprocessor or microcontroller. And when you develop a microprocessor application on FPGA, that microprocessor can accomplish any sort of code, running from a basic Python code and running from any artificial intelligence code using Python again. So robotic applications and satellite communications, communication device. Satellite communications best example is Chandrayaan 3. In the Chandrayaan 3 architecture, they have used heavy electronics using FPGA architecture. FPGA is also the part of their architecture in the electronics and communication devices and heavy machinery industries. So heavy machinery industries in the automation, like if the series of chains or a series of belts in the product manufacturing, they use some set of machineries using FPGA, and FPGAs can be widely used for testing purposes, and they only check. So for the ultimate checking of the process, if the process is done by hundreds of microcontrollers and the motors and drives, and those all the equipment can be verified by using FPGA again. So there are set of different applications going around the use of FPGA. So you can dig around and you can understand each one of them. Then coming to the first project, we have developed AND gate, very basic functionality. What we have checked is, we have checked the timing simulation using like if you see the clock in the output, if it is 0 0, the output should be 0, and if it is 0 1, the output is also 0. So let us take two inputs and one clock, and 0 and 0, and this is A input, and this is B input, and this is output. So in the A input it is 0 1, and B is 0 0, both can be 0, and now it is again 1 0, and now for 0 it can be 1. Let us take the inputs, and 1 1, and now it can be 0 again, and this can be 0 again, and for the ultimate purpose, now it can be taken as 1. Now it is 0 and it is 1. So according to the AND gate functionality, you can take, when the two inputs are 0, output is 0. One input is 0, 1 0, it is 0, and this is 0 again, 0 1, it is 0, and 1 0 is 0, and 0 0, it is 0. Now both the inputs are high, both the inputs are 1, then AND gate is 1. So this is how timing functionality you can check, and we have made some timing simulations as well in the using of AND gate. And in the same way, we can also run for the OR gate, that is in the second project example. So I'll take it there. So in the second project, what we have developed is OR gate and simulated it by using the timestamps, and then we have generated the bit stream. What we have learned in the project 2, we have generated the bit stream. Then in the project 3, we have developed a block RAM onto the chip. So basically, in the personal computer boards, in the motherboard, you can see chips that can be fitted on this hardware architecture. So this is not a chip. This is the pins that your motherboard can be connected. In one of the pins can be going to USB module. So if you connect the chip, and that chip can be connected to this pin, and this pin is internally connected to USB port. So you will understand the hardware architecture as well. And after the regular simulations, we generate the bit stream. In the previous designs, we have written HDL code and we have generated bit stream in the entire development flow. But in this, we have taken IP integrator and we have taken example as memory block, block RAM we have called BRAM. So for that we have generated test bench as well. We have used test bench and we have generated output, and then we have generated bit stream for that IP. So in this project, major thing is we have introduced ourselves to the IP integrator. So that is again a major part. Now come back to the uh, last project that we have done a few days ago. So that is developing a soft-core processor called microblaze, and microblaze processor architecture is nothing but it has taken from the RISC architecture. RISC is a well-known architecture now in the embedded systems wherever you use. So in that RISC, one example is microblaze soft-core processor. One another processor is nothing but alternative to the microblaze processor is Zinc boards, uh, ZYNQ. So Zinc boards are the examples that you can use in alternative to the microblaze processor. So this is again taking the IP module that are already available. IPs are nothing but intellectual properties developed by the different vendors, and we collect those IPs together and we develop a design using that IP module, and it is mostly done by the EDA automation. Hence we develop our application within few hours, so we can check the functionality as well. And then with the microblaze processor, we also try to test the hello world program in C programming, not the HDL programming. So with the HDL programming, we have developed the IP, we have generated the IP model, and then we have tested it using C programming, though we don't have hardware in our hands. So hence we have done 4 projects as of now. From tomorrow we will be developing Verilog HDL as well. So recap on the EDA tools. EDA definition is nothing but electronic design automation. So this is a software application tool where we run the flow of the FPGA development flow. So development flow, and these EDA tools are essential for writing our own scripts and executing the design with more number of complexity in terms of lakhs of transistors available in the logic cells. So that is the importance on EDA tools. It's a simple recap, guys, today. And yeah, as I have told, complex chip design industry uses EDA tools for making their process easy, and we majorly focus on developing the functionality and testing the functionality. So designing and verification. So design, verify is the major key steps in the development of chip design. So billions of standard cells. Standard cells can be any sort of elements like logic cells, for example, AND gate, OR gate, XOR, any type of logic cells or flip flops can be used to refer as a standard cell. Now coming to the EDA scripting languages, these are there are two major EDA scripting languages that you should be knowing in the industry. One is Tickle scripting, one is Perl scripting. So again, what is the difference between Verilog HDL or VHDL in par with Tickle scripting is, Tickle scripting is nothing but set of commands to execute. So it tells the EDA tool to go this go to this file, use this file and develop this file, and uh, stop the execution flow. So the commands that we use to run the EDA automation are written in the Tickle scripting and Perl scripting. Don't get confused, guys. VHDL or Verilog HDL is used to develop the architecture on the FPGA chip, and by using this VHDL file, and you take these input files, constraint files, .xdc file or .vhdl file, you can take these all files and embedded in the EDA tool. Now you should give some commands to the EDA tool, and those commands are written in the language called Tickle, tool command language. So Tickle is nothing but tool command language in the scripting. So TCL has set of commands. So in the previous lectures, we have also used some report IP status. In the report IP status, we can see the license available for the IP. So that kind of commands, report timing, report IP status, all these set of commands are nothing but used to execute the EDA functionalities. So we are giving instructions to the EDA tool, not to the design. So now EDA tool will be operated according to this set of Tickle commands. So then essential topics to learn after this entire training, right? I would suggest you should be knowing all these protocols: UART, I2C, SPI, HAMBA protocols like advanced higher bus, high speed bus, and advanced this APB and AXI address bus. So USB protocols, PCI protocols, and then complex memory controllers like DDR, DRAM, dynamic RAMs, and DDR1, 2. All these are the latest versions of the technology. So if you can go through these protocols, if you can understand what are these protocols, how they are implemented on the architecture of FPGA, so that will be your sure shot point to get selected in the interviews or in the job placements. So please make a note of this. Understand one after the other. Most of them will be familiar in a simple way. So if you take UART, I2C, and SPI, and if you take these AMBA protocols and then USB and PCI, then complex memory. So you can check 1, 2, 3, 4. So these four, if you go through these four set of protocols and if you can understand in that way, it will be uh, very useful and you will be selected very quickly. Like you will be the sure shot choice to get selected. So then this is the FPGA again, you can see. And now coming to any questions, you can shoot out to the questions. And I'm really happy that some of you guys are so seriously learning and you have come across the entire video and shooting out the questions to me in the WhatsApp. And I am happy to solve all of your queries. And thank you guys for attending everyday's class. And we'll not be delaying any lectures from here and all. So thank you. Jai Hind.